Hello. We're going to talk about neuromorphic processing in this presentation, specifically Intel's Loihi 2 architecture. So, current processors, they mainly rely on substantial amount of energy sources. It uh, it gets quite inefficient as the time and space complexity increases, and it includes high loads and loads of energy to for consistent operations, money, and carbon emissions. For example, world's first exascale supercomputer, Frontier at Oak Ridge National Lab. It uses about 21 megawatts power, and if you convert it into megawatts per hour, it could actually run 25 average US household for a month. And the laboratory inside is about 680 meters square. And by the way, exascale supercomputer means this computer can perform computation about 10 to the 18 computations per second. Um, so if you compare it to the human brain, it could compute about 10 to the 16 to the 10 to the 19 computations per second, and it will utilize about 1,000 kilojoules per day. If you convert it into calories, it only needs about 250 calories to perform all these computations. And what would that be? About half a Chick-fil-A sandwich? So comparatively, human brain computes computation power is about a billion times more efficient than the fastest supercomputer we got. So what is the solution? So in the late 80s, Dr. Carver Mead, he was an electric engineer who first proposed the idea of utilizing the concept of biological neural networks on the hardware side. So in the 1950s, people came up with this idea of artificial neural networks that we used in on this mainly on the software side, that computes complex nodes to perform all these computations. But what about the implementing this on the hardware, on the 3D three-dimensional chip? So that is what the idea is about, mimicking the hardware of the human brain on a three-dimensional chip, so-called neuromorphic processors. So current implementation mainly utilizes a type of neural networks called spiking neural networks that is usually utilizing the idea of the of neuron spikes in the biological networks. So more recently, Intel has come up with an idea and a team. They spread a team to work on a processor called Loihi chip that is further explored in this presentation.
And this brings us to the concept of the Loihi chip. In short, Loihi is a 14 nanometer neuromorphic research test chip created by Intel in 2017. Initially, the first generation chip was called Loihi and was created with 128,000 neurons that were capable of using this new spiking neural network, which allows the neurons to dynamically program themselves. So you can think of it as a form of pseudo machine learning network. This spiking neural network allows the processor to simulate the concept of synaptic learning, which essentially means that both the learning algorithm and the learning rate of the Loihi chip can be modified at any given point. And in 2021, Intel released their second generation chip in the line, simply called Loihi 2, which is the focus of our presentation and report. Loihi 2's biggest upgrade over its predecessor is the fact that it now has a million neurons instead of 128,000. Now, to quickly overview the architecture of Loihi 2, once again, it is based on that spiking neural network architecture that we mentioned previously. It takes a lot of inspiration from the first generation chip in the sense that it shares the same base architecture as Loihi 1 and has the same number of neuron cores at 128, but ends up with 3 more processors than the first generation chip. Loihi 2 also uses Intel's x86 architecture. More specifically, it uses their 32-bit instruction set architecture.
Loihi 2 supports fully programmable neuron models that mimic the biological neurons found in the human brain. And these neuron models describe the behavior of neurons through short sequences of microcode instructions. The microcode instruction set, which can be seen in the table on the right, supports typical instructions such as bitwise and math operations, conditional branching, and memory access, but it also supports specialized instructions for spike generation and probing.
Now let's dive deeper into the processor architecture. As stated before, Loihi 2 is almost an exact derivative of its predecessor Loihi in terms of its architecture. The key difference between the two is that Loihi 2 scaled back the size of the chip by 2 times. This size difference has allowed for Loihi 2 to contain twice as many processors, 8 times more neurons, and 4 times more bandwidth per chip-to-chip link. Specifics of the processor architecture include the parallel off-chip interfaces. These interfaces serve as chip-to-chip links that support the standard asynchronous protocols. Next is the neuromorphic core, which is the hub for the programmable neuron model and where its learning takes place. This core holds up to 128 kilobytes of synaptic memory. Then we have the microprocessor core, which is responsible for the data encoding, data decoding, and network configuration of the spike-based communication.
Loihi 2 allows the architecture to support new classes of neuro-inspired algorithms and applications, which provides 10 times faster processing, 15 times greater resource density, and improved energy efficiency. Loihi 2 achieves 2 times higher synaptic density than Loihi. It has slightly less aggregated memory, and the core capacity is significantly higher because the memory architecture is more efficient, as shown in the figure. It supports flexible memory partitioning to increase the proper core capacity. It also aggregates its memory to allow different function in the core to access a variable number of memory banks, which results in a higher effective core capacity. Loihi 2 also offers advanced connectivity features to utilize the available memory better. More significant improvements come from Loihi 2's support for convolutional, factorized, and stochastic connections. It increases the number of processors from 6 to 3, and the advanced processor count helps to prevent this conventional processing task from bottlenecking overall application performance. Loihi 2 also supports 3D multi-chip scaling, resulting in shorter routing distances between chips and reducing inter-chip link congestion.
Intel researchers have created a nose using the Loihi neuromorphic research chip. When exposed to the scent of a chemical, the electronic nose becomes familiar with the specific scent and is able to recognize it from then on. When other distracting smells are present, the nose can still correctly specify the chemical that it is looking for by its scent. The Loihi chip was constructed to be similar to the way that neurons work in the olfactory bulb. That's the part of the brain that can sense what the nose is smelling. The Loihi chip can also be used to test if toxic substances are in the atmosphere, to seek out potential bombs, drugs, or explosive objects by using the smelling feature. It can also help in diagnosing medical patients. Thank you for listening to our presentation. And here are our references.